Hello everyone, and today we are coming to the next section of this lecture, which is atomic origin of magnetism. So our job for today is to understand what actually gives magnetic properties to a solid body, to refresh some of our knowledge from atom physics, and to work a bit with to introduce different parameters which are usually used in this field of science to be able to understand the following material. And before we will go on, let me present you once more this nice book of Professor Krishnan, Fundamentals and Applications of Magnetic Materials. It covers not only materials, but also physics of magnetism itself. Therefore, yeah, I can recommend it. And as you can see on this slide, it's a periodic table of elements. And it's slightly different because here there is a color code. So in green, we see the materials which are called diamagnetic. So we will consider this in next lectures. What is this? But usually it's considered to be like non-magnetic. Then in white, there is paramagnet. So you see how many paramagnetic materials are here. These are also not that what we get used to as magnets, but they show some magnetic behavior. Then we have ferromagnets are shown in red and antiferromagnet in gray. Besides, there are temperatures. Here for ferromagnets, it's Curie temperature, Tc, and for antiferromagnets, it's Néel temperature, Tn. So these materials show properties, ferromagnetic or antiferromagnetic properties for temperatures which are lower than Curie or Néel temperatures. And you can see here. So, the materials to which we get used as to magnets, with which we were playing when we were kids, are ferromagnets. And you see that from whole amount of elements which we have in nature, only few of them are magnetic. And till the end of the course, we have to understand why is that. And to start explanation, we need to consider the model or standard simplest model, Bohr model of atom. Hydrogen atom, where we have positively charged nucleus and one electron flying around, have a circular trajectory. So this electron, it has a charge. This is just constant, 1.610 to the power minus 19 coulomb. And you pay attention that I have here positive charge, yeah? So because I will be using minus everywhere where it's needed. The value E is positive, and then it's rotating, it's flying around rather fast. The period of its rotation is around 10 to the power minus 16 seconds, very fast. And the radius, it's a Bohr radius, it's 5 10 to the power minus 11 meter. Why it's important? Because such electron can be considered like effective current loop. And the current, by definition, it's an amount of charge which is moved per time period. So in our case, it's simply charge of electron divided by the period of rotation with a sign minus because electron is negatively charged, as you know, and it gives us rather large current in milliamp range. It's so large simply because rotation is very fast. So it's yeah, this time is very small. As a result, current is getting very large as for one electron. But this is just to give you a brief understanding that there is some associated current. And then as we started in the electrodynamics, this current loop will create a magnetic moment. And magnetic moment, it's a vector which is oriented perpendicular to the plane of the loop, like it's shown here. And its magnitude can be found simply as a current multiplied with the area of this loop. Then what you can do, you can easily calculate it. So current we have defined here, just a period t we have replaced with angular velocity or angular frequency omega. Therefore we have here charge omega 2 pi, and area here is simplest formula PR squared. This is our value for magnetic moment. And as you see, it has minus sign because of electron. So we have magnetic moment. It's clear now that magnetism is the simplest Bohr model of atom is coming from rotation of electron since it is charged. And nevertheless, we should not forget that electron has a mass. We all know that mass of electron is rather small. Nevertheless, it exists. And if there is a mass and you have object flying along the circular trajectory, you will get angular momentum, which can be found as linear momentum mass multiplied with linear velocity, and you multiply it with arm r. Again, this is just this is vector in general, but here without vector, it means that this is magnitude. And again, instead of linear velocity, you put circular velocity omega, and you have such value for the angular momentum. And immediately you can see that here there is no charge, so this one is positive, and it means that angular and magnetic momenta are pointing in opposite directions. Like it's shown in the figure, means pointing down, L is pointing up because of the negative charge of electron. And now comparing this formula and this one, we simply, for example, take omega r squared from each equation and make them equal, you will get very fundamental and important ratio between magnetic moment and angular momentum, known as a magnetomechanical ratio, which involves only fundamental constants. So here magnetic moment of electron, we replace and in further this mu L. We will use later mu L because in the next slides we will see that magnetic moment, that electron itself has spin and associated magnetic moment. In order to distinguish moment given by the orbital motion of electron and by spin, we define here L. So L means orbital. So this mu L then is coupled to angular momentum LE with this constant E over 2 ME. We sign minus, which points us that they point in opposite directions. So now coming back to, so this was all classical, besides the fact that electron is rotating here, yes? Because we know that if you will try to describe it in classical physics, electron when it's rotating here is flying along the circular trajectory, it always has acceleration. And in this case, it should emit energy. And it means that after some time, it should drop down to the nucleus. Nevertheless, it never happens. Our atoms are stable, as we know from our life. And this is the answer to this, gives us quantum mechanics. Yeah. So besides that, this nuclear is this atom is stable. Here we need quantum mechanics. And nevertheless, all these formulas which we just did were just standard normal physics and classical physics. And now we are coming again back to quantum mechanics because we know that energy as well as orbital momentum, angular momentum of electron in atom should be quantized. And quantization, then we can get the following formulas. So magnetic moment given by the orbital motion of electron can be found like this. Here's then our constant, E over 2 ME, square root L, L plus 1. So, and L is a orbital quantum number, and H here is a Planck constant. Then what you do, this constant, you replace with a famous magneton Bohr. Yeah, so principally this is magnetic moment, mu B E to ME, which is equal around 9 × 10⁻⁻24 ampere per times meter squared. Good, so now we have quantized orbital momentum. We know where it comes from, and we can move on. Before we will continue with spin, I would like to make a little detour and present you the experiment where principally this fundamental formula was proven experimentally. The point is that here we are talking about so-called Einstein-Degas effect. The idea was very simple. So as you can see from the title, you know who did this experiment. I think it was 1915, before discovery of spin. So people, in reality, in this experiment, they measured magnetic moment related to spin of electron, but it was not discovered yet. Therefore, they were thinking they were measuring particularly the orbital magnetic momentum. But the idea is that this formula clearly shows us that angular momentum is coupled to magnetic momentum. Then what you can do, you can create such a metallic rod, a magnetic rod of iron, for example. You put it inside a coil, and when you send electric current, DC, as we know, we will generate Ørsted field. So this will be kind of solenoid, and you can apply field pointing in one direction or in the opposite direction. And in such a case, you can change magnetization. So magnetization is a total magnetic moment of your body. And you can magnetize it up or down. It means that applying current, you can change magnetic moment, which is coupled to orbital moment. And then the question, what's going on with orbital momentum? And it should go somewhere. And in order to conserve it, it goes to the orbital momentum of the whole body. Therefore, what happens, you apply current, you change magnetization, and all this magnetic moment, this body starts to rotate. That's why, especially done on such a in such a special way experiment, that it's easy can be rotated in one or other direction. So that's what the Einstein-Degas effect means. And to get a bit deeper, I would like to show you this experiment, this nice YouTube video. In the University of Michigan, which will show kind of their lab demonstrator of Einstein-Degas effect. Since the effect is small, they are not applying here DC, but instead they are applying AC, so alternating current. They do not put solenoid on top of your of the cylinder, but just it creates with such a large solenoid the field, and they switch it one direction or other direction. So they constantly switch magnetization direction of this cylinder up, back and forth. And the reason behind that, in such a way, this mechanical object has some resonance frequency, yeah. And if you will choose proper frequency of change in magnetization, then even with very small force in one direction or another direction, you can slowly increase precision. So you can get very strong, pronounced effect if you use resonance. And that's exactly what they're doing here. So you can see that really just change in magnetization direction of this cylinder, they were able to rotate it. So they really coupled magnetic moment to orbital momentum of the whole body, like it was done in the original experiment. Great experiment, and we are moving on. And the next what I would like to speak about is spin. So slightly later, people discovered that magnetic moment comes not only from the orbital motion of electron, but also from electron itself. Spin is not so easy to understand. You need quantum mechanics here for sure. It's not a classical effect. And nevertheless, if you just to get it easier, you can imagine it as follows, that orbital momentum is like a motion of Earth around Sun. The Sun, and spin momentum is rotation of Earth itself. Yeah, so Earth rotating and kind of creates a spin. So pretty often you can find this kind of picture when it's really like electron, which, for example, a sphere with distributed charge, and it rotates and it creates then a current around, like a current loop, for example, like we have seen in the previous case. Nevertheless, we keep in mind that origin of this effect lies in quantum mechanics within a relativistic framework. So this picture is physically is not wrong. It just helps you to understand. So what do we know? We know already that spin is an angular momentum, spin angular momentum. We define it usually with S, and exactly the same way like it was shown in the previous case, we can define an magnetic moment, mu, S, which is associated with spin, with angular momentum. Here staying the same factor, but here is staying in additional GS. G is a spectroscopic splitting factor. Experimentally, it's found that a gyroscopic splitting factor is almost 2. Therefore, pretty often you can find such formulas that magnetic moment associated with spin is given 2 magneton Bohr S plus 1. And you can ask why we didn't have it for orbital momentum. Principally, you also should, strictly speaking, should place there spectroscopic splitting factor for orbital momentum, but it's experimentally measured that it's 1. So now we have magnetic moment, and we know that it's also quantized as everything in quantum mechanics. And again, coming back to the understanding what is spin, we should keep in mind that it is not a current loop, but for all practical purposes, it behaves like one. What is the meaning of practical purposes? It means that, first of all, it generates a magnetic field, which is similar to that of magnetic dipole. So it really makes a field. And second, in an external field, it experiences a torque. So if you will put your spin within magnetic field, magnetic induction B, it will feel a torque. Therefore, principally, it behaves like a current loop. Only the nature of it is purely quantum mechanical. Again, for better understanding towards about discovery of spin. The spin was discovered in this famous Gerlach experiment. And since it's a discovery, pretty often it happens that they were searching for something slightly different and discovered spin. In this particular case, they were trying to check, I think it was 1926 or somewhere, maybe a few years earlier, and they were searching for experimental proof that angular momentum is quantized. So these were the times when quantum mechanics already there were. It was one of the theories, and I think there were more than one theories. It was still not fully clear if it exists at all, if it's this quantum mechanics works or not, and the general idea of quantization, and they wanted to prove it. And that was the experiment. So what they, nevertheless, at that time they didn't know spin, and they were looking towards the orbital momentum. As we have seen, there is orbital momentum of electron, which also should be quantized. At least there you can find different different sources in literature, but that's what I could understand, because if you will look on this original paper from their paper, it's staying here ML. L is usually associated with orbital, yeah, and they expected 3 states, 0, 1, and -1. So they expected that if you will take an atom with 1 electron rotating, then you should get 3 possibilities, 3 states, quantized states for this orbital motion. And they have chosen silver atom. Silver atom, it was a great choice, because if you will look on the crystallographic structure of silver, you have all these orbitals are fully filled. For each electron point spin up, and you have electron spin down, which was not known at the time, but they knew that if shell is fully filled, then it's more or less, it's not sensitive to anything. But there is only one, this 5s electron, and they wanted to study properties of particularly this electron. So they were working with neutral atoms, therefore you can send them through magnetic field without Lorentz force, and you will more or less measure only this. What they did know at the time that s orbitals have orbital momentum equals 0. Therefore, principally, it was not possible to measure orbital momentum of this electron. This we know only now. But what you can measure momentum of spin itself. Yeah, that's what they finally seen. So the experiment was performed the following way. They have here oven with melted argentums with silver, which is then was evaporated, and then it moves through such slit plates in order to create a narrow beam of neutral atoms, and afterwards it flies through this magnet. So here you see magnet, it's specially created in a way, and this was probably the most complicated at the time to realize experimentally, magnetic field with a huge gradient of field. So it means that it should change. Why gradient is important? Because potential energy of magnet on board. Yeah, so if you take magnetic moment, smallest magnetic moment magnet or board, if you put it in the field B, you will get some potential energy. Nevertheless, in order to split your beam, to force your neutral atoms to move somewhere, you need force, and force is gradient of potential energy. And in this case, it means that since you cannot have gradient of magnet on board, you need gradient of magnetic field. That means that you can split this beam into parts only if you apply gradient of magnetic field large enough, and they managed to do this. And when they performed experiment, they have found, as you can see by the way here, they have found that their beam is split into two parts. So if quantum mechanics would not work, they would see just one large spot. Because from quantum mechanics, when you have different magnetic moments, not quantized to magnet on board, but just any arbitrary value, then you would have maximum in center, and then such a normal distribution. If they would measure magnetic moment from orbital momentum, they would have 3 peaks, but in experiments they have found 2 peaks, and this was a discovery of spin. Let us have a look on this nice movie which explains it nicely.
The Stern-Gerlach experiment, performed in 1922, delivered the first experimental proof of the fascinating degree of freedom of an electron spin. A beam of silver atoms was generated in an atomic beam furnace. It was then sent towards an inhomogeneous magnetic field. According to classical physics, one would expect the magnetic moments of silver atoms to be randomly oriented. They should be deflected in the inhomogeneous magnetic field by different amounts, depending on their orientation. However, the researchers observed that the beam was split in 2 possible states, which were later named spin up and spin down. How can this be explained? Let us first analyze the electron configuration of a silver atom. One silver atom has a total of 47 electrons. In 46 of these electrons, each spin up is paired with one spin down. The spins neutralize each other. There is only one unpaired spin, the spin of the 5s electron. It can be either in spin up or spin down, or in any superposition of these 2 states. We can represent this spin state using a Bloch sphere. The spin can point in any random direction. The spins of all silver atoms are randomly distributed. They are therefore not polarized. In fact, there is a close connection between this experiment with a single electron spin and the experiment with single polarized photons. Here, the polarizing filter corresponds to the inhomogeneous magnetic field. Just like with photons, in a single experiment, it is completely random whether the spin points in the direction of the polarizing filter or in the opposite direction. The result is a black and white random pattern. Let's have a closer look at the quantum mechanical measurement process in the Bloch sphere. The spin has some arbitrary orientation before it interacts with the inhomogeneous magnetic field. The inhomogeneous magnetic field acts as a filter. It is presented here as a slot. It forces the spin to take a random orientation, either in line with the inhomogeneous magnetic field or in the opposite direction. If the basis state is close to up, it is very unlikely to change the direction in down. However, it may still do so. When performing their canonical experiment, Stern and Gerlach were unable to use single silver atoms. Therefore, they could not demonstrate the role of chance in each experiment. However, they were the first to demonstrate that the spin is quantized, or separated in up and down. It was a sensational achievement in their time.
Okay. So, and now I would like to just a brief summary from that what you know already from atom physics. So, if we are trying to describe some atom, we have to speak about the following principal numbers of each electron. So first of all, we have principal now quantum number usually shown with n, and it shows the number of orbital of shell. Then we have orbital angular number L, which we more often use as S orbital, P, D, and F orbital. And there is a azimuthal quantum number, a special quantization number ML, which changes from minus to plus values, so 0, plus, minus 1, plus, minus 2, and so on. And as we have shown, there is orbital magnetic moment associated with orbital motion, which we put as mu L. And then after discovery of Stern and Gerlach, there is also spin of electron, which is 1/2 usually, and ms quantum number is plus or minus 1/2. Then spin magnetic moment of electron, so it means magnetic moment associated with spin of electron itself, can be found as this mu s gs e. So this is magneton Bohr s. So, or you can rewrite it. Here what's important also in this table is that here is magnitude, which we discussed before. It's length of your vector, but in most of the cases we are speaking about z component. So we project everything to the direction of field, for example, to that axis. And here you see how large is magnetic moment associated with a single spin. And you can see that here are staying two values, ms and gs. Gs we have discussed in previous slide, it's around 2, and ms is plus minus 1, 2. So it means that magnetic moment associated with the spin as that component is equal to magneton Bohr. So the message from this part is that magnetic moment in our solid body comes from electron, from its orbital motion and from its own nature, from spin. You can ask, but come on, there are also nuclei in our system, there are protons, neutrons. Why do we ignore magnetic moment created from these particles? Because, as we know, both protons and neutrons, they also have spin. And the answer you can see immediately here, because if you will consider this formula, but you will put instead of here, you will have also spin. It might be different from spin of electron. Nevertheless, it's the same, let's say the same order of magnitude. But what's important that here is staying a mass of your particle. So magnetic moment is always inversely proportional to mass, and mass of proton and neutron is bit more than 4 orders of magnitude larger than the mass of electrons. Therefore, magnetic moment, which is coming from nucleus, is usually simply ignored in most of the experiments, but not everywhere. For example, if you will use resonance technique, like we have seen in this Einstein-Degas laboratory experiment, then you can get feedback from magnetic moment from nucleus, and this is all intensively used in magnetic recorded resonance imaging, MRI, magnetic resonance imaging in medicine. Particularly there, you measure magnetic moment not from electron, but from nucleus. Okay, and we are moving to the last slide in this part. And I would like to say speak a bit about the definitions which I'm using in the course. I simply take the same approach which Krishnan defined. I like it. So he's usually, when he's speaking about magnetic moment of electron, he's using mu, and magnetic moment is measured in units ampere meter square. If we have to talk about magnetic moment of atom, then we use m small, the same units. And then we need to introduce such very important parameter as magnetization. So magnetization is a total magnetic moment. So you just take your body, you summarize all magnetic moments, of course, vector, taking into account vector, because these two magnetic moments will cancel each other and total magnetic moment will be 0. And you divide it by the volume. And that's why if you will look on unit, ampere meter square divided with meter square, you have ampere per meter. This is a unit of magnetization. So it's a vector sum of the individual magnetic moments per volume. Good. And in this course, we will, most of the time, we will talk about such a parameter, which is named magnetic susceptibility. So here you see magnetization, which is total magnetic moment of your body. And here it's a ratio of magnetic moment divided with magnetic field H. And magnetic susceptibility is such a parameter which gives you the, it shows you how magnetic body reacts to applied magnetic field. For example, you have situation that you apply magnetic field and nothing changes. Your magnetization was 0, so there was no magnetic moment. You applied magnetic field and there is still no magnetic moment. Then the susceptibility is equal 0, and you can say that your material is not magnetic. Or if you see that when you apply field, your magnetic field, your magnetic moments start to point in the same direction, so you will get net magnetization, and your chi is more than 0, and then it's magnetic material. So the susceptibility is such a nice factor, and as you can see in this table, so this is a very nice table which summarizes all main physical properties which are used in magnetism terms. Gives you units, and it gives you units in CGS. So this is old centimeter gram second system, and more and more used SI standard system of units. And if you will look now on M and H, so field H we measure in ampere per meter, and magnetization we measure also in ampere per meter. So it means that units of chi is it's unitless. Now I would like to bring your attention to this very important formula and to speak a bit about unit systems. So you see here are two parameters, B and H. First one is named as magnetic field H, and second one is named magnetic inductance. So I should warn you that there is a certain mess with all this terminology, because depending if you will check English-speaking literature, German-speaking literature, Soviet Union books, you can find the different authors define slightly different. I think that's what is written here. It's the most commonly used, and I will try to stick to this name. So this B is magnetic inductance. Nevertheless, you can also find such a way that people simply say magnetic field H and magnetic field B, which is also, I think, understandable. And what is the physical meaning of this formula is that, let's look here, it's easier. So this is above, it's written in SI system, and here's CGS. So if you look on CGS, we see the following, that magnetic inductance B is equal to applied external magnetic field H. So this is the same field if you will have some material or you put just vacuum, or there is nothing, this will be a field H. But if it's not vacuum, but you have some medium, some body with magnetic moment, then you will get here magnetization. So it means that B, it's kind of the total field created by that what you applied and by the field created by the body itself. Therefore, B is equal H plus 4PM. And I start especially with CGS because in some sense it's more physical. You can understand that if you have vacuum, you have no magnetic moments, you just cancel this term, and then your field B is equal to field H, which is absolutely logical. Yeah, there is nothing else. Your field is equal to your field. And nevertheless, these are still different parameters, H and B. And H is measured in Oersted in CGS and B in Gauss. Nevertheless, it's one Oersted is equal one Gauss. So that's the way how they overcame. And now if you come to SI system, which principally makes things much easier in many cases, because yeah, there is a chaos a bit with all these units, and SI really does a great job. And now I see that all new books are written in SI units. For example, if you will read solid state book of Kittel, which is kind of Bible of solid state physics, he's still using CGS, old school, and all new books are written in SI units. So I also will try to use SI in the process, of course, of this course, but you can see that if you will take your vacuum, then there will be difference between B and H equal to this non-physical permeability of free space with some value, with some units. And that's why people who get used to CGS do not like SI. Nevertheless, we can easily work with both systems if needed. And then you just reproduce mu1, and you can introduce such a parameter which is named here. For example, here again, it's easier. So you can just replace your M with H high, then you will get such value. And then this 1 plus 4p high, where high is susceptibility, you will get magnetic permeability. Permeability, here's the name, and this is how it looks in CGS, and the same you can do for SI units, but then you will have mu0 and mu-r permeability. Yeah? Good, so these are two parameters. We will mainly speak about susceptibility, but you also have in mind that there is another parameter, permeability, which is coupling magnetic field H and magnetic inductance B. Let's go again a bit through parameters. So magnetic field H we measure in Oersted or ampere per meters. 1 ampere per meter is 4 pi 10 to the power minus 3 Oersted. Magnetic inductance we measure in Gauss or in SI in Tesla. The ratio is 10 to the power 4. So then magnetic moment we discuss, magnetization we discuss, permeability. Then also it's important that here you have, for example, in this table, why I like it, we have, for example, such important issues like torque, which is created on when you put magnetic moment M and you put it within the field, magnetic field, then you will get torque. In CGS, you've searched it like a cross products of M with field H, but for SI it's M with cross product with inductance B. And potential energy is the same. First of all, do not forget about this minus MH, scalar product, minus MB for SI units. Good. And here again, you have these formulas which we already discussed. Yeah. So I think that's it. Now we have all the instruments which are needed in order to understand the next part about diamagnets and paramagnets.